At the picture you see a meander, which is just a simple closed curve in the plane transversely intersecting the horizontal line. And of course you consider meanders up to natural equivalence. According to Landau and Zwontkin, who have one of the nice surveys about meanders, the notion was suggested by Vladimir Arnauld, though the meanders were studied already by Henri Poincaré, and they appear in physics, they appear in biology. Well, really nice object. And one of the problems is counting problem. How many meanders do you have? You impose the limit on the number of intersections with the horizontal line, and you ask how many meanders do you have? The problem is open. There is a conjectural formula, but which was conjectured by physicists, well, actually by this group of physicists about 20 years ago, but the problem is still open. I want to suggest a sort of partial solution of the problem in some regime. When you have an object like this, well, there are several natural things which you can do. First, you can chop your picture by this red line, and you get two arc systems, one on top and one on the other. And the second thing which you can do is when you have an arc system like this, you can compactify your half plane or compactify a plane here, and you imagine that this line is just infinite line. So from a plane you get two hemispheres. The red line becomes a closed line, it's equator, and you get two arc systems. So this collection of arcs become arc system on northern hemisphere, and this collection of arcs becomes arc system on the southern hemisphere. And you can encode, you can impose sort of a topological passport of this picture by drawing a dual graph to your arc system, like these black lines correspond to dual graph, and you have to imagine they have really very many blue arcs, so you will have very many pieces like this, these fogons. It is natural to suppress these vertices of valence 2 and to consider only interesting vertices. And then you will have finite number of these interesting vertices. So you have, in this case, where in genus 0, so instead of graphs, we'll have just trees. So this tree with suppressed vertices of valence 2 would record the combinatorial passport of meander. Now, it is much easier, it is not difficult to imagine that it's much easier to count arc system on a disk. This is a relatively simple problem. The trouble is that when you glue two arcs, so you have one arc system on northern hemisphere, another arc system on the southern hemisphere, and then you can choose a twist to glue them together, and sometimes you do get a meander like here, and if you choose another twist, you get a multi-curve. So our red curve is our former horizontal line, and blue curves come, well, this blue curve provides you a meander, and here we have several connected components. So let us discuss first the following thing. So let us impose some restrictions. Let us impose the restriction for the number of arcs. Let's fix these combinatorial passports, which are top tree and bottom tree, which are responsible for the meander. And let us consider all possible arc systems with little n arcs, which is bounded by some huge constant n capital on upper hemisphere, on bottom hemisphere. Let's consider all possible identifications, and let's compute sort of probability to get a meander. We divide all triples like this giving rise to meander over all possible number of different triples. So the question is what one is supposed to expect from this probability. So how this probability tends to 0 as a power function, as exponential function, and if it's a power function, then what is the exponent depending on combinatorics and so on. So any guesses? Actually, it does not tend to 0. For me, it was quite surprising. To my mind, it's sort of counterintuitive. You have enormous amount of arcs on top and on the bottom, and with a with a non-zero probability, you get just a single connected curve, which covers everything. And this limit is computable. Here's an example. So for this example which was on the picture, the probability is this exact number, which is approximately 1/3, so which is not even quite small, right? And there is, for any pair of trees, the answer depends only on the total number of vertices of valence, 1, 3, etc., and is given by explicit formula, which I don't want to give. It is a bit, well, it is not that important what exactly is the explicit formula. It exists. I want to give it in slightly different setting. Let us simplify the combinatorial passport of Meander. Let us record only the number of univalent vertices, the ends of our trees. And consider now all possible, so you fix the number of these ends. Let us call it by P. And let us consider all possible trees which have exactly P ends in total on top and on the bottom. And let us, so this is the probability to get a meander from this kind of trees. So this is the exact answer. And in red, there are objects which I did not define yet, but which have geometric origin. So here we will have the volume of certain moduli space, and here part of this volume. They would appear slightly later, but this is just to convince you that this simple-minded explicit formula comes from geometry. And now let us come back to meanders. So I discussed probability, now let us count meanders. So I want to distinguish meanders of two types. So here, a meander on the left has this maximal arc, which is sometimes called a rainbow, which goes from the very left endpoint to the very right endpoint. And meander on the right doesn't have an arc like this. And as a parameter, I will use, well, it is clearly analogous to the previous parameter P, the number of ends of the tree, the number of these minimal arcs, which are colored in black here on the picture. So there are 5 minimal arcs here, 5 minimal arcs on the right. And let us count meanders of each of these two types. So the number of meanders with at most n capital arcs having these 5 black minimal arcs and with a rainbow is called M plus, and without a rainbow is called M minus. So again, a question. So what is your expectation? Would we have, so I fix, so here we have P equal to 5, here we have P equal to 5. So whether this number would be larger or that number would be larger. If you are forced to give an answer just without thinking, well, you say, here we have an extra constraint, right? One might have less meanders of this type. Again, this is sort of counterintuitive. So here is, if you do not look at this first line, just look at the second line, the growth rate of number of meanders of this type is a, well, power function in n. This is the explicit coefficient for this polynomial asymptotic. And again, this explicit coefficient is computed in terms of this red quantity, which is not defined yet and which would have geometric origin. And it would appear in a second. And notice that the number of meanders with this minimal arc grows as n power 2p minus 4, while without minimal arc only as n power 2p minus 5. So this number gains. They're roughly n times more meanders of this type. Okay, this was sort of to make publicity of geometric objects which would appear in a second. And these geometric objects are volumes of moduli, of corresponding moduli spaces. To introduce very fast the corresponding moduli spaces, let me construct the object which is the point of corresponding moduli space. So let us consider a broken line, more or less arbitrary broken line composed from several vectors in the plane. If we construct another broken line starting from the very same point and using the very same vectors placed in different order, then of course two broken lines, if they start from the same point, they get to the same point. And if we are minimum lucky, we get a polygon. They do not self-intersect. Note that being lucky is an open condition. I can move a little bit any vector and it will be still a polygon. And again, clearly something should depend on permutation which we apply here, but this is not a rare situation when we get a polygon. But I like surfaces more than polygons. So I will now suggest to identify the corresponding sides of this polygon because they are clearly distributed into pairs, and in every pair we have two sides which are parallel and have the same length. So we identify them by parallel translation. And we get an algo of a flat torus, right? How do we draw a flat torus? We usually take a rectangle or a parallelogram and we identify opposite sides. We get flat torus. Here we get, in this particular case, we'll get a perfectly flat surface of genus 2. And note that, similar as for the torus, when we identify two sides by parallel translation, there is no singularity of flat metric on the edge. It would disappear like for a torus. Don't worry, there is no contradiction with the Gauss-Bonnet theorem because this flat surface has a conical singularity. All vertices of this octagon in this particular case would be identified to the same point, and this point will have conical angle, which is in this particular situation will have angle 6 pi. So all troubles with curvature are hidden at this point. Now, I note that I really insist that we're working not with polygons but with surfaces. Because the very same translation surface which we obtain by gluing this corresponding pairs of sides can be unwrapped to a polygon in many different ways, because you can say if you glue a surface from this polygon, you take a pair of scissors, you can chop out this pentagon, and since this side is glued to this side, you put it here. So the surface obtained from this polygon and the surface obtained from this polygon is the same surface. There are plenty of representations, and this shows why we have sort of a modular space right away. Note also the following. I will use it in a second. If all vectors which we use here are integer vectors, then we can tile the corresponding surface with unit squares. It would be a square tile surface. If they are rational vectors, it would be also a square tile surface, just tiling would be tiny squares. It would appear shortly. Now, note one more thing. I will introduce it in two different ways. So we have a family of surfaces defined in this way because we can deform vectors, and it should sound plausible that these vectors play role of coordinates. These coordinates are complex coordinates because every vector you can consider as a complex number. And also, by convention, we impose a tiny extra structure. I want to keep track of direction of the vertical direction. So the surface obtained from this polygon turned by 25 degrees, for me it's already different flat surface, different translation surface. It is sort of polarized. And very last observation is that, so we have 4 coordinates. We just consider a naive volume element, and actually it does not depend on coordinates. If you make this kind of transformation and use the vectors of a new polygon, it would be the same volume element because transformation is very particular. Now, a synonymous description of the family of these translation surfaces. So we can imagine that since we know what is the direction to the north, we know how to place our polygon in the complex plane up to translation. our complex plane is endowed with a complex coordinate z, and the gluing rule for the sides of the polygon is if you take a local coordinate near one side and near the other side, they are related by local coordinate z prime is equal to local coordinate z plus constant. This is extremely holomorphic transformation. So we get complex structure on the surface. To be very accurate, one has to verify that we have to puncture first the conical singularities and then make an exercise in complex analysis to verify that complex structure extends to these points. It does. That's not all the structure because, well, when we glue a surface from this polygon, we do not have global coordinate anymore. But if we consider dz, because of this kind of gluing rules, dz is equal to dz prime. So we get a perfectly well-defined holomorphic one form on the corresponding Riemann surface. And once again, initially it is well-defined on the surface where we take out their conical singularities, and then you verify this holomorphic one form extends to these points, and these points are just zeros of the corresponding holomorphic one form. So basically, I tried to convince you that this moduli space or family of flat surfaces with given combinatorial geometry is the same as moduli space of pairs, a complex curve C, and a holomorphic one form on this complex curve, where the holomorphic one form has extra restriction. It has zeros of prescribed multiplicities, m1, etc., mn. As for any holomorphic one form, sum of the degrees of zeros is equal to 2g minus 2. And this moduli space is modeled by the first cohomology of the surface relative to the collection of points. So this number of points does not change. We always consider only forms with exactly n zeros of this kind of degrees, and we take this cohomology with complex coefficients. So the coordinates which we used in the picture with polygon are exactly the same, because what are these vertices of the polygon in this language? That's what is the complex number which corresponds to a vector? It's the integral of the form dz over the corresponding segment, meaning that we get relative periods of our holomorphic one form with respect to this finite collection of points. Now, this space is still too uncompact, because you can multiply, you can apply proportional rescaling of your flat surface, or what is the same, multiply your holomorphic one form by a number. So the reasonable way to make it at least a little bit more sort of compact is to impose, for example, the restriction for the area of the corresponding flat surface. This restriction in terms of periods is just quadratic relation, so we impose this condition, and we get sort of a unit hyperboloid in the ambient space. Now, we get, I already mentioned that we have natural volume element. In this language, it can be defined as follows. So our space is modeled on the vector space, and inside this is not an abstract vector space, it's cohomology. So inside this abstract vector space, we have a very natural integer lattice, just cohomology with coefficients z plus iz. So when you have a vector space, you have plenty of volume forms defined up to multiplication by a real number. As soon as you have a lattice, you know how to scale the corresponding volume form. You just impose the condition that the fundamental domain of your lattice has volume 1. So we do have a distinguished volume form, and that's exactly the same volume form which was defined naively as just Lebesgue measure in the corresponding space. And when you have a volume form in the ambient space and the level hypersurface of some function, then you get induced volume form on this unit hyperboloid, and that would be, for me, well, and the volume of the corresponding unit hyperboloid with respect to the induced volume form would be the volume of the corresponding moduli space for me. It's called Masur-Veech volume, and the theorem of Masur and Veech says that the total volume of any stratum like this, of abelian, or similarly one consider quadratic differentials, is finite. Now, how can we are taught to compute areas and volumes in school? So first remark, it's not the school, it's sort of the normalization coefficient. I need to compute sort of surface area of a hypersurface, and it is related to the volume of the corresponding cone just by dimensional factor. So this is first remark. And the second remark is that to compute the volume of the corresponding cone, which is based on this unit hyperboloid, one can consider a small grid and just count the number of rational points in this grid and then normalize, and in the limit you get volume. And since everything is homogeneous here, we have scaling parameter, we can, instead of considering surfaces of area 1, this unit hyperboloid, we can consider a larger hyperboloid and transform our small grid to unit square grid. So basically the problem of this volume computation is the problem of how many translation surfaces you can find when translation surface is constructed from unit squares and when you are allowed to use at most n squares. So this is exactly the computation of number of integer points in this shaded area. Now, what are geometrically points these points of our grid? So by definition, in this language, that's the point which are represented in this period coordinates by points in this lattice. And they're covering over standard torus R2 quotient by z plus iz, because you can send a point P of your surface to this complex number. So you fix one of the zeros, you take any path joining your point of the surface which represents a point of this lattice. So if you have translation surface representing a point of this lattice, then you take any point already over the surface, you join it by some path to distinguished point P1, you evaluate integral of your holomorphic one form, and you take it mod z plus iz. Since all periods live in z plus iz, this number defined, evaluated mod z plus iz is already well defined. This is the point of a standard torus. We get a ramified covering, and the ramification points of the cover are exactly the zeros of omega. So this is the description in this language. And now let me come back to the naive language. So basically, you are given a game like this, you are given 1 million pieces like this, and you are asked how many animals of this kind you can construct from this number of at most this number of pieces, when there is an additional restriction on number and types of conical singularities. So this is the counting problem, and actually it is sort of particular case of counting Hurwitz numbers. We're counting torus covers, or in this case, we're covering pillowcase covers. So it's really sort of a version of Hurwitz numbers. Now, the first theorem about these volumes was already mentioned. It's the theorem of Masur and Veech saying that volumes are finite, but they were computed later by 20 years later by Eskinokounkov and Pandaripanda, and they used the following smart observation. As always, when you are counting something, it is very useful to introduce some generating function, and when you are counting objects of this type, it is very natural to use as a weight 1 over automorphism of the order of finite automorphism group of the corresponding surface. So usually it is just 1, but from time to time it's different to 1. So rarely the square tile surfaces are more symmetric than others. And then you have to use this weight. And then you count all of them in this way, introducing this formal parameter, and they prove that this corresponding generating function is a quasi-modular form. And in particular, it is possible to use this to prove that any volume is pi power 2g, where g is the genus of the surface, times rational number. So computing volume means compute numerator and denominator as integer numbers. So really explicitly compute. It is not that easy, Askin implemented this theorem to an algorithm which allowed to compute these rational factors for all strata up to genus 10, and for the principal stratum up to genus 200. And based on these calculations, we developed a conjecture on a very simple asymptotic formula, and this conjecture is partly proved very recently by Chen Muller and Zagir, who constructed certain more elaborated generating function. But still, there are two regimes, so it's possible to compute volumes explicitly when genus is small. The asymptotics of this volume, in some cases, is already known due to this work. In some cases, it's guessed, and I hope that they would extend it to these cases. But the only situation where the computation is simple and given by just explicit formula for the volume is genus 0. Genus 0 is always easier than higher genera. So in genus 0, Kontsevich stated a conjecture about the formula for the volumes using some arguments from dynamics which at this time sounded somehow strange, and at this time we could never imagine that it would be the only proof which was found, because everything somehow were upside down. Volumes were intended to be used for dynamics, and still, up to now, the only proof of the formula of Kontsevich is, well, uses certain kind of dynamical arguments. It is so simple that I want to give an answer. So, define a function over an integer number greater than or equal to -1 as follows. So it's n double factorial, where this is the product of all numbers n, n minus 2, n minus 4, etc. And here another double factorial like this, times pi power n times some correctional term which depends on even whether n is even or odd. And for -1 and for 0 we define it by hands as follows. Then the volume of the corresponding stratum of quadratic differentials with simple poles and zeros of degrees, of given degrees, is given as the product of this over this partner which tells what zeros and poles do we have of this function v with some universal constant 2 pi. So it is not that important what exactly is the formula. What I wanted to show is that it is more than explicit. There are no algorithms. You do not need to use tables of characters of representation of for symmetry group and so on. It's just simple-minded explicit formula. And now I want to cite something from dynamics, which comes from dynamics. So this is once again an example of square-tiled surface. And notice that horizontally any square-tiled surface has horizontal leaves which are all closed. So it is glued from several maximal cylinders. At the border of the cylinder you have conical singularity, so there is some bifurcation, and then some other cylinders start to grow. And one can count the number of cylinders, of maximal horizontal cylinders from which is glued square-tiled surface, and it can vary from 1 to something like genus plus number of singularities -1, so the range is reasonable. So every square-tiled surface carries this extra characteristic, the number of horizontal cylinders. So in this sense, integer points in our space, they have this sort of extra coloring by the number of cylinders. One can compute contribution of square-tiled surfaces having separately 1 cylinder, 2 cylinder, 3, etc. So I took the stratum where I have one conical singularity of angle 4 pi and another conical singularity of angle 8 pi. And here you have from 1 to 4 cylinders. And that's the list of contributions. And I can tell that the only one which is really easy to compute is the one which corresponds to 1 cylinders. Which is not that surprising because after all, instead of complicated combinatorics of the surface. You just have one cylinder. And then you have to tell how subintervals on top are glued to subintervals on the bottom. At least it should be imaginable that it is much easier combinatorics than gluing many cylinders together. And now to the theorem. So recall this picture with a flat surface glued from a polygon, and imagine that we deform a little bit every vector to have a neighborhood in the space of our flat surfaces, and we can consider a small grid in this neighborhood, taking vectors which have rational coordinates. They would produce square tile surfaces with tiny squares, and we can count how many out of these squares represent one cylinder, two cylinder, three cylinder, and so on. So when you deform your surface, the number of cylinders can vary drastically because you tile your surface with tiny squares and you will have very long bands wrapping around the surface. So it's not that the number of cylinders behaves sort of strangely under deformation. And here is the first theorem. The asymptotic proportion of square tile surfaces tiled with tiny epsilon times epsilon squares in any open domain and having exactly k maximal horizontal cylinders does not depend on the open domain. It's one and the same everywhere. It's the same as for their asymptotic proportion for the entire stratum, the ones which were shown at the previous slide. This is the first theorem. So this is sort of, this can be viewed in a sense in the following way. You consider an open domain, you subdivide it by a very small grid, and you take a random point of this small grid, and the probability to get a surface with exactly 3 cylinders does not depend on the open domain. It's just the same as sort of the probability to take in this sense a random square tile surface everywhere and to get 3 cylinders. And the second statement is the following. If we consider vertical directions, we'll also have cylinders. We'll have not horizontal cylinders, but vertical cylinders. And the statement is that the number of cylinders, in a sense, do not correlate. So if you consider only surfaces which horizontally have 35 cylinders, and consider, and now study, well, this distribution and look how many vertical cylinders do you have. They do not know that they have 35 horizontal cylinders. The asymptotic distribution would be the same. So in this sense, sort of the conditional probability to get k cylinders when you impose that vertically you have g cylinders is the same as just forget this extra condition. Okay, now this already gives the way to compute volumes approximately experimentally. And the idea is the following. First, we can compute all square tile surfaces having single horizontal cylinder. We discussed this is sort of easier problem. This one can compute explicitly, and for small genera, this is really some of their characters of representation of symmetric group and Frobenius formula, and for large genera there is a very good approximate formula due to Don Zagier, which is sort of simplification of his computation of orbifold early characteristic of moduli space. So simple is sort of relatively simple, meaning there are simple formulas. So still this is sort of quite doable. And then you just take an open domain in your space which is convenient for you, and you take many random square tile surfaces and just experimentally collect statistics. How often do you see one cylinder square tile surfaces? So this gives you two numbers. One is contribution of one cylinder square tile surfaces to the volume, which is computed explicitly. And 1 is probability to get one cylinder square tile surface, which is computed experimentally. You divide one over the other, and you get very good approximation for the volume of the moduli space. It is precious because there are plenty of conventions on normalizations in this story. And this is, to my mind, basically impossible not to lose some factor of 2 from the very beginning, going from the very beginning to the very end. And when you know approximate values of volumes, you would not lose factor of 2. Now, you can lose 10% or 5%, but you wouldn't lose integer number. This was really precious. And now also I can suggest you a solution of this meander problem. So the first step is to recognize the familiar object in a pair of transverse multicurves on a sphere. So I have, instead of just two curves, let us consider collections of curves. So we have collection of red curves on a sphere. They do not intersect between each other. And we have collection of blue curves on a sphere, and they do not intersect between each other, and they transversely intersect with red curves. So let us consider the dual graph to this picture. I'm claiming that we'll get a thing like this. It is easier to get in backwards direction, and then you will see how to go here and, well, to and fro. So let us consider square tile sphere. Then I can consider a red curve, horizontal red curve passing through the center of every square, and I will get a red horizontal line. And I will consider a blue curve passing through the center, which would be vertical. So by construction, red curves, which are horizontal, do not intersect between each other, and blue curves, which are vertical, do not intersect between each other, and all intersections are transverse. And so these two pictures are actually synonymous, and this very simple-minded observation is basically the key of our approach to meander problem, because, well, I don't know, to my mind this is somehow funny. You just have a purely topological structure, pair of transverse multicurves on a sphere, and then you touch it, transforming your polygons into squares, and you get very rich structure. You get structure, well, you get complex structure on the sphere, and you get God-given quadratic differential, which is responsible for this thing. Okay, so to count all pairs of transverse multicurves, we have to count all possible square tile surfaces. Now, the next idea is what are arc systems? Arc systems, all possible arc systems, they correspond to the situation when we have a single horizontal multicurve, well, and certain amount of vertical. So our horizontal multicurve is not a multicurve, it's just a single connected curve, and vertical is some curve. So they correspond to square tile surfaces having horizontally only one cylinder. And what are meanders? That's the square tile surfaces which have one single horizontal cylinder and single vertical cylinder. And we can count 3 out of these numbers. We know how to count all possible multicurves because it's counting of all possible square tile surfaces. This is volume of the corresponding moduli space, and you have seen that the answer is very explicit and given by a formula. Also, it was mentioned that it is easy to count one cylinder, just horizontally one cylinder square tile surfaces. So we have 2 out of 3 quantities related by this non-correlation of horizontal and vertical distribution. So we know that this number of horizontally one cylinder and vertically one cylinder surfaces is expressed asymptotically in this way, and we get the answer. And the very last remark is that fixing the number of these minimal arcs, we fix the number of simple poles of quadratic differential, and actually all graphs which have vertices different from valence 1 and valence 3 correspond to smaller strata and only the principal stratum survives, the stratum where you have only simple zeros. And for this stratum, the answer is particularly simple. And let me finish the talk with one more story. So for 20 years, I was envying my colleagues who are computing Weil-Petersson volumes because they could use intersection theory, and finally we realized that it is also here. Let me start with formal introduction of objects, and then it would become hopefully understandable. But formally, let me introduce the following object. So I consider the moduli space MGN of Riemann surfaces of genus G with n marked points, and I consider any ordered partition of 3G minus 3 plus n, which is dimensional of this space. So I have a partition like this, and then I define a polynomial in n variables, b1, etc., bn, which would be polynomial actually in squares of these variables, in the following way. I take these variables power 2d1, 2d2, etc., 2dn. This is this thing. And the coefficient is expressed in terms of this characteristic number defined in terms of psi classes with some combinatorial coefficient. So I know that half of the audience are experts who know way better than me what are psi classes and what is the tautological ring and things like this, but just a reminder, so if you have a moduli space like this, so it's moduli space of marked Riemann surfaces, you can choose, and they are numbered. We attribute the numbers to our marked points. We can choose point number 3 and consider cotangent space to this point at our Riemann surface. And then you deform this Riemann surface and your cotangent space starts to deform. So you actually get, for free, a line bundle over MGN. And you can consider the first, and this line bundle is a holomorphic line bundle. You can consider the first Chern class of this holomorphic line bundle. It's called psi 3. 3 because we took third marked point. If we would take first marked point, it would be psi 1. And now when you have n classes of degree 2, you can take product of them, power d1, etc. And if you check this condition, the powers are chosen in such a way that this product would be exactly their top class. So the class of degree, which is dimension of this space, so we can integrate this thing over there. Moduli space, we get rational number. So we get tons of rational numbers like this, and I use them to construct these polynomials. They are quite famous because they appear everywhere, in particular in Witten's conjecture, in Mirzahani's formula for, this polynomial is the top homogeneous part of Mirzahani's volume polynomial, providing the Weil-Petersson volume of the moduli space of bordered Riemann surfaces. Now let me introduce a formal operation which associates associates to a homogeneous polynomial in number. I just take powers of variables b and replace them by the corresponding power factorial, and I multiply by zeta of this power shifted by 1. So to every polynomial like this, to every monomial like this, we associate a number, and then we extend it to symmetric polynomials in B's by linearity. Now let me apply it to surfaces. So for example, here I consider surface of genus 2, and here we have a list of all topological classes of primitive simple multicurves on surface of genus 2. So when we have only one connected component, the only invariant is whether it's separating or not. And when we have several components, we have several other multicurves, you can consider them as sort of partial Pans decompositions defined up to homeomorphism of the surface. Now, as soon as we have structure like this, I can do the following. I cut the surface open. And for example, in this particular case, I get a surface of genus 1 with two boundary components, which would be of the same length B1. And I evaluate this polynomial. I multiply it by B1. And here there are two extra factors. One, as usual, is responsible, the red one, for the symmetry of the corresponding configuration, for the order of the symmetry group. And the blue one is particularly simple-minded. It's just 1 over 2 power number of connected components minus 1. So here we have only one connected component after opening up. So 1 minus 1 is 0, 2 power 0 is 1, that's why we have 1. Here we have two connected components, so we have 2. Here we have two connected, so everywhere else we have 2. So, and when there are several connected components, you take products of the corresponding polynomials. Then you apply that's the values of these polynomials as true polynomials in B. And then you apply the operator, so for example, here we have polynomial coefficient times B1 power 5. Recall that we transform this polynomial into a number in the following way. We take this 5 factorial and we take zeta of 5 plus 1, zeta of 6, we get a number. So now let us sum up the numbers of the resulting numbers. Theorem. What we get is the moduli space of the Masur-Veech volume of the corresponding moduli space of quadratic differentials on genus 2 surface with of the principal stratum of quadratic differentials on this genus 2 surface. So I will make a formal statement in a second, but to make a formal statement, I want to use a coding of this kind of surfaces with graphs. So on the previous slide, our surface didn't have mark points. Mark points in interpretation with hyperbolic metric give rise to cusps. So a torus with 2 mark points gives a torus with this hyperbolic metric and 2 cusps. And a decomposition of surface by a single curve like this is encoded by a graph, and probably from the picture it is already visible what I am doing. So every marked point is encoded by a half h. So the graphs are dual graphs to this decomposition. So the vertices correspond to connected components. I have to record what is the genus of the corresponding connected component. For example, here when I cut it open, I have genus 1 on the left, genus 0 on the right. B1 is the weight which is associated to the corresponding h. And now I can formulate the theorem that Masur-Veech volume of the corresponding stratum of quadratic differentials, so genus G, simple poles and n simple zeros, n simple poles and otherwise simple zeros, is expressed in terms of these polynomials. Now, 2 remarks. First, we realized that this theorem for n equal to 0 is actually already proved by Mirzakhani, except that you have to glue 2 theorems from 2 different papers of Mirzakhani, and she just didn't bother to do it. She knew that the formula is like this. For her it was obvious. And the funny observation is that while Peterson volume of MGN corresponds to constant term of Mirzakhani's volume polynomial, while we are interested in the top homogeneous term of the same volume polynomial, so it's sort of the opposite regime when all the length of, so she is interested in the situation when she contracts all boundary components and replaces all b's in this polynomial by 0. And we're interested in exactly opposite regime when all these b's are very large in the top homogeneous part. Okay, and now I'm almost done. So this is the picture of Mariam, and I should say that actually she was all the time in my talk, because we were we tried to find an argument for this equidistribution theorem and for things like this for about 20 years, and then rereading papers of Mariam, we found a passage which is just 2 paragraphs and which is dealing with something different, but the idea applies just straight away, and the proof is extremely easy. And this last years, this is a constant feeling that we are sort of following her traces, and it's like, I don't know, she already prepared many things and she was to do it herself, and unfortunately she didn't have time. And here so the last thing is the following one. I would like to cite a result of Mirzahani, which I absolutely love, and which has a counterpart in these counting problems. So here are our main actor, square-tiled surface. Here it's a square-tiled sphere. And on the left picture you have a hyperbolic representation of this thing. So I associate to these corners which have cone angle pi, they correspond to simple poles of corresponding quadratic differential, and in the language of, in this other language, they are marked points on the surface, and in the language of hyperbolic geometry, we're supposed to put cusps there. And so we have 7 corners like this, and this picture 1, 2, 3, 4, 5, 6, 7. We have 7 cusps. The curves in black here are exactly the horizontal curves which we draw, which pass through the center of the square, except that I have, since here we have our flat cylinder of height 2, I have to take this curve with weight 2, and here we also have, so we'll have a curve here and a curve here. I also put weight 2 here, and we can encode all this by a graph, as a graph just before, which is dual graph to the corresponding system of multi-curves on the surface, and we have to tell what are genera of the corresponding vertices and to put these weights. And now the theorem of Mirzahani. So she counted the number of simple closed hyperbolic geodesics on surfaces of given type. So you fix its genus, you fix the number of cusps, and you fix the type of your simple closed geodesic. For example, in this picture, if you take a single simple closed geodesic, it can separate a sphere with, so here we have spheres with 3 cusps. It can separate a sphere with 3 cusps in 3 plus 3 cusps, so 3 cusps on one side, 3 cusps on the other side, or 4 cusps on one side and 2 cusps on the other side. A hyperbolic geodesic cannot separate a single cusp, because otherwise it would contract to a cusp, and it cannot separate no cusps, because again it would contract. So that's the only 2 situations, and she proved the following thing. So she counted these types of simple closed geodesics separately. So you fix hyperbolic surface X, you count this kind of hyperbolic closed hyperbolic, simple hyperbolic geodesics of bounded length. You impose some bound for the length, and you divide the one number over the other. So Mirzahani proved that this ratio does not depend on hyperbolic metric. So for me, it's completely astonishing, because you can deform the surface enormously, right? You can create very narrow bottlenecks and very long hyperbolic cylinders. There are plenty of room for deformations, and still, no matter what is particular hyperbolic geometry of the surface, the corresponding ratio is one and the same for all hyperbolic surfaces in this family, and it is expressed exactly as, well, in terms of the numbers as before. And now the claim is that fix any, so instead of single simple, you can consider just simple closed curves, You can consider multi-curves. Why not? Of course, the theorem, well, the result of Mirzaghani is more general. It is formulated for any multi-curve. And the claim is that if you consider not simple closed hyperbolic geodesics, but simple closed flat geodesics, then the corresponding asymptotic proportions are exactly the same if you give reasonable sense to the counting problem. So you impose this multi-curve gamma, and you count how many square tiled surfaces of bounded length which correspond to this multi-curve you can find, meaning that you impose the heights of your horizontal cylinders and topology of decomposition into cylinders, you get exactly the same proportions. Thank you very much for your attention.